Hello, my steel design friends. In our last couple of videos, we've developed and set up some expressions for the basic Euler buckling load as well as the effective length factor corrections that can be applied to that. In this video, I'm going to show you the AISC requirements for designing columns. They're based off of the research and the equations that we showed you, but there's some modifications that we have to make. So we'll talk about a few factors with those, and then how do you start to design a column using the AISC methodology. So that's the purpose of this video. Without further ado, let's get started. All right, in the 15th edition AISC Manual of Steel Construction, we find the requirements for column design located in Chapter E. Because basically nothing says column or compression like the letter E, right? Maybe it's because it's based on Euler, I don't know. But anyway, this is where it's at. It's 16.1-33 is the general specification. And then, pull these pages out here real quick. 16.1-307 will be the commentary. But you'll also want to pay special attention to then this Appendix 7, which contain the alignment charts, okay? And that's back here in what would be Appendix 7, okay? So it's not in any of the chapters. It's kind of an extra known as the alternative methods of design for stability, okay? And this is where we were finding our K factors. This is where we found our alignment charts, and we'll talk about the alignment charts here in the next video, kind of how we use that to further correct our effective length factors. But that's where the effective length factors is back in there. All right, everything else kind of follows the same general format. Gray pages are the commentary, and here are the actual rules and requirements. Okay, so we'll kind of run our way through this. The first thing that you notice is that the phi factor for LRFD methodology is 0.9 for columns, so it's just the same as what was the tension member, and the 0.9 should make sense because this is kind of a yielding phenomenon that we're looking at. We're not worried about a rupture limit state usually, so 0.9 is a pretty good statistical value for phi. Okay, there will be some other things that will come in, and then we get into some rules on effective length. Okay, and then I want to point out these two notes here, that for members designed on the basis of compression, the effective slenderness ratio L over R should not exceed 200. Okay, now the reason for this is explained back in the commentary, but what typically happens from a standpoint, this isn't a strength requirement, but what happens is when you get to an L over R that is that is greater than 200, your column is becoming very, very slender and very narrow, and it's kind of spindly, and it becomes very difficult to handle. It's hard to pick up with a crane. You have to pick it up in multiple points, and you can get damage to it just by the very act of placing it into position. Okay, so we want something with a little bit of strength and stability to it, and that's where this requirement comes in. And now again, I guess you don't necessarily have to follow it, but it is a recommendation here in the gray pages. Okay, all right. So we can also, they also say that you can use other methods to find K, whether it's through experimentation or whatever. You don't have to follow their K values, but you do need to be able to prove the K that you're using. So most of the time we just use the theoreticals or the recommended values that were back in that Appendix 7. Okay, so the basic expressions for the buckling of members without slender elements on this are given by this. And so what we're looking at is the rules that they're writing for compression are not just for columns, they're also for plates and for stiffeners and any part of a member that is subjected to compression and the behaviors that we can expect to have happen on those. Okay, but the general meat of what we're going to follow is just a simple column, and those two phases that we talked about when we were looking at our elastic stress curve in the last video. We talked about an elastic buckling phenomenon where it followed Euler pretty close, and then an inelastic buckling phenomenon where it kind of did its own thing. These are the two regions that AISC is going to have us try to observe. Okay, and both of those are contained down here in these equations below. Okay, so the basic strength capacity equation, Pn is equal to a critical stress value times Ag. Now this FCR is the FCR for buckling, okay, or for a material failure. So what we do is we look at, it's not necessarily the same Euler equation, but it's based off of experimental research, but FCR is defined down here for both of these. Okay, so what happens is when L over R is less than or equal to 4.71 times the square root of E over Fy, so again, that's kind of a constant term for the grade of steel, the limiting value is said to be 4.71 times that factor. Okay, when that happens, then, okay, or if Fy over our Euler stress is 2.25, okay, that we can come in and we can write an expression for FCR as being 0.6582 that Fy over Fe equation multiplied by Fy. It's a function of Fy where this guy is always less than, should always be less than 1.0. Okay, and most of the time that is what will happen. Okay, this is considered to be the inelastic state, okay, for inelastic columns. Okay, when it's over that same limit, when it's greater, the slenderness ratio of the column is greater than that limit, if you will, then the formula changes a little bit. It's FCR is equal to 0.877 times this F effective, this Fe value that we have happening there, okay? Where Fe is the Euler buckling stress. So we're scaling it down for inelastic. So you can see we take an Euler stress and then we set it at about 0.87, or if you look, that's close to 90% of Euler. Okay, so it's kind of like an implied phi factor on that as well. So it's not quite Euler, but it's close. Okay, this is where the inelastic is happening, and it's significantly different. Okay, now in other textbooks and other sources, you may see that spelled out in a different way. Okay, if you flip over to the next page on here, this is where the Euler equation is given. It's pi squared E over L over R squared. Now recognize they've left off the K correction factor. This is assumed for pin. So if we decide that we have a different scenario, as we talked about in the last video, where maybe it's fixed, or it's got a little bit of rotation, but it's not truly free, we'll need to include a K in this equation, all right? So everything we do with columns is a KL over R. Okay, whenever you see L over R, just mentally make a note that it should be KL over R to account for that in columns. Okay, and then we'll show you what we can do with those formulas as well. All right, so that's kind of the code and where we're going with this. We'll come back in a second with this and show you some other notes. Okay, all right, so that's what we're doing. Now, some textbooks will write this a little bit differently, okay, in which we calculate the Euler stress, okay, and then I can define a parameter lambda as being the square root of Fy over Fe. Okay, in which case this lambda then becomes KL over R times the square root of Fy over pi squared E. Kind of gets us to our formula like this. And so now we have a function of involving our KL over R again to be able to plot, our basic stress versus KL over R, okay, as a function of the slenderness ratio. So again, Euler strength is this curve. Okay, that's what follows in the elastic region. And then in the inelastic region, we're going to be limiting that to a fairly constant value, not quite constant, but fairly constant value there. The only thing that changes in these other textbooks when they write it this way is that instead of being Fy over Fe like we saw in the code, you may see this written as a lambda c squared. Okay, it's kind of a compactness criteria almost for columns. Okay, and so you may see that may pop up from time to time in literature or journal articles or something. You may see that. So I'll point that out just kind of as an FYI. Don't be thrown. The one thing that's nice about it is that when we write it as a lambda term, when this expression is less than 1.5, okay, it's the same thing. That is the inelastic criteria, okay, or that Fy over Fe is less than or equal to 2.25. That's the basis. So I can calculate this guy and then compare it to what my actual KL over R is, which we said, and if that is less than or equal to 4.71 square root of E over Fy, then I know that I'm in an inelastic behavior. I'm down in this region for my strength. Okay, so this lambda value is a little bit cleaner, but this is the criteria as it's written in the code. Okay, so depending on what your preference is or what you understand, for my students, we'll just stick with the KL over R, but for the others, I just want you aware that this is out there as well. Okay, and so those are our basic formulas. Okay, so that's what we're doing. So everything we do is going to be a KL over R check. So here's that effective length factor. L is the length of the member. R is the least radius of gyration. Okay, now for an I-beam, which most columns and buildings are typically made out of W shapes or some wide flange shape, you know that there will be an RX and an RY associated with that. So you have to calculate KL over R for both directions. And in fact, depending on the framing conditions, you can have different lengths of columns in each direction. Like say you brace it in one direction but not in the other, you know, well then it's harder to buckle in one way. You can actually, you know, add additional strength to the member by manipulating these K's and these L's such that, you know, it may not be an RY that controls like we always said was the case in a tension member. Okay, so there's some trickery that we can do here, and we'll show you that in one of these examples here in just a second. Okay, so now if I'm over that 1.5 limit, or over KL over R is greater than 4.71 square root of E over Fy, that's our elastic column equation, and that was the one that was 0.877 times Fe, or 0.877 over lambda c squared multiplied by Fy. Okay, so that's our basic critical stress for the elastic region. These are the two formulas I just showed you in the manual. Okay, so kind of a different way of writing it for what we're doing there. All right, so let's give one a shot, just kind of our first try out there, and see what we can see, or see what we can conclude. I have an example here, okay, that I want to select the lightest A572 grade 50. If you want to call this as an A992, I'm cool. It's the same grade of steel and the same methodology. Okay, so for a W section, it's got 95 kips of dead load, it's got 100 kips of live load, and the column length is L equal to 16 feet. We're going to go with the pin case on this guy. Okay, so for this is going to tell me that our K is 1.0. All right, so the first thing that we have to do, we've got to factor the loads. I'm going to assume that it's the 1.2 dead, 1.6 live is the one that's controlling. But again, you would want to check all the combinations out of the AISC, SEI 7 load combinations. But for this one, just for the sake of this argument, we're just going to do the 1.2 and 1.6. So if I plug these numbers in, 1.2 times 95 plus 1.6 times 100, I get a load of 274 kips. That's a factored load that I have to design for. Okay. The next thing I do is I then figure out what is my effective length factor. Okay. And so for this was a pin scenario. So we're going to take K is equal to 1.0. Okay, so then my K times L is going to be 1.0 times 16 feet times 12 inches is 192 inches is my length. Okay, so what we want to do when we're kind of designing this is we want to kind of look at, well, the problem that we have is we don't know what the size of the member is. I don't know the area and I don't know the radius of gyration. Okay, and so this is where we're going to cheat a little bit and kind of think about, you know, normal situations for normal loads in buildings. For most buildings that are normally framed with columns that are 25, 30 feet on center, and, you know, with normal framing and normal loading, our column sizes generally fall within the range of a W8, W10, W12, or W14, kind of as a guess. Okay, and often they have a weight that's kind of what we call a mid-range value, it's kind of around 50 pounds per foot. A W12 by 53 is a very common shape. Okay, it's all kind of around this. So we're going to just for the sake of argument, just for testing this, we're going to take a guess and say, let's try a W10 by 49. This is a shape that's fairly close. Again, it's just a kind of a shot in the dark at this. Okay, if I look this member up in my steel manual, okay, we're going to find that RY is 2.45 inches and RX is 4.35 inches. Okay, so what we're going to do is we take the worst of the two, because we're assuming that L is the same in both directions. Okay, and if I do that, then I have 192 inches over 2.5, gives me a KL over RY value of 76. Okay, obviously if I put RX in here, this number gets even smaller. Okay, so this is, you take the highest KL over R as your limiting value as you start to do this. Now let's compare that then to 4.71 times the square root of 29,000 over, I can't quite see that, that's a 50. And I have a residual number happening here. Okay. That if I plug in a 50 KSI into this expression, this is that 4.71 limit that we had. Okay. We get a value of 113.4. So what that tells me is that my 76 is less than this number. Okay. And when that happens, we said that tells me that this is an inelastic buckling problem. Okay, it's not the Euler loading that's going to be the failure. It's going to be kind of a start of a material failure. Okay, and so if we look at our basic chart again, what that's saying is that this is the line that was the 4.71. All right, so for our case, that was 113.4 on there. We're plotting over here somewhere. Okay, that's where my strength is. Okay, so we're up on this curve as we start to look at this KL over R ratio. Okay, all right, so that's good news from a strength standpoint. Okay, so now all we do is we can kind of come in and plug this in. That should not be 133.6, that's 113.4. 113.4 is the limit. Okay, and so now we can come in and we can compute the critical stress. Okay, so we're going to take our inelastic formula, 0.658 raised to the Fy over Fe. Okay, and my Fy being multiplied by Fy, then we'll calculate our Euler stress from the Euler formula, pi squared E KL over R squared. It's going to tell me that my Fe is 49.5 KSI. Okay, we know that Fy is 50 KSI. Okay, so we're less than the proportional limit, so we're okay. If this number comes out greater than the proportional limit for some reason, then you've got to be careful to limit this value. You've got to be a little bit mindful of that. Okay, so if I plug all of this in, then basically 50 over 49.5 is basically 1.0, and so this formula becomes 0.658 raised to this quantity times Fy is now 0.655. So we're changing the third decimal because we're so close. So this is, we're basically getting the full strength out of this. It's just barely on the edge of wanting to buckle. Okay, and so if I do that, then I can plug our math in, and so my critical stress for this is 32.75 KSI. Okay, so that would be my critical stress for the column. Now you'll notice that, again, we took kind of a guess on R for our particular shape. So now let's go through and verify if our assumption is correct. So we can solve for the area associated with this, AG, as being then phi PN over 0.9 times F critical. Okay, that's just a rearrangement of my basic AISC formula. That's a rearrangement of the formula here, right? A gross times the critical strength. Okay, so we've taken kind of a guess at what the critical strength is for that column on there, and you can see that we do 274 kips over 0.9. Okay, and then divided by 2.75 KSI. Okay, will tell me that my gross area on this is going to be 9.29 inches squared for this W10 by 49. Okay, so now if I take a W10 by 49, I can actually calculate what is the design capacity. 0.9 times 14.4 square inches, that's the AG value of our 10 by 49. Okay, multiplied then by our stress, and that is the wrong value. Whoops. 32.8 KSI, it should be that number. Okay, but the math on this is 424. So I fixed it there, I just didn't fix the equation. So 424 kips is the capacity of this W10 by 49. Now if you compare that back to my factored load, we are well above it. Okay, so a 10 by 49 is probably a little bit over designed, but this is the approach for using the equations to be able to design for those particular values. Now, you can see that it's a little bit of trial and error. We have a problem that I don't know R and I don't know A, so this kind of follows that design methodology we talked about in tension members, where you kind of guess both and then get a size, but this becomes a bit of a sticking point that we're guessing, and my guess happened to be way far off, but that's how the equations are used. Okay, in the next video, I'm going to show you how we could use some design tables in the AISC manual to speed up this process very significantly. Okay, and we'll talk about that in the next one. All right, now, obviously, that's a bit over designed. I would probably want to try something, a little bit lighter. So maybe I only need a W12, or sorry, a W8, or a lighter W10. Whatever the case may be. But we could kind of recalculate FCR, FE, KL over R, and AG by trying another size. Okay, or you can automate it. This is a real good one to put into like a macro or a program that contains the AISC tables. You could actually kind of iterate through and find the fastest one. Or I can show you another method, and I will show you two of those in the next video. So we will talk to you next time. Happy engineering.